I think sound is alright. So let's first start with what we are today will be doing is the linear regression part. So in linear regression, we will be looking at simple linear regression, and then we will be looking at multilinear regression. Then we will be looking at other consideration in regression mode. And for this, like we will be seeing the part of the some of the things using the stats perspective, and I would highly recommend the book from the Trevor Hasty and Robert, which has a really good an introduction for the stats learning. You can use with R if you prefer for the code, and if you want to use it with Python, you can do it also. So we have first is the simple linear regression, and the next part will be going to be the multilinear regression part. And last we will see the other consideration in the regression model we have. So without like further like wasting any time, we will just see it. So what we basically need for the part of this, and this is going to be a fast revision, and uh, I would assume like you should know the knowledge of basic stats and probability, and the basic stats is not from the high school level. I would prefer if you could able to grab some of the concepts from the college or universities level, and you can use some of the free resources from YouTube to basically learn about these concepts. Uh, Mostly these stats concepts in the regression revolves around like variance or like mean you should know, and there are some of the distribution functions you should be able to see. So distribution is also, so you should know how of the graphs you are able to see. So you should be able to know about the Poisson distribution or about the regression distribution. Any kind of model you are going to build is going to be based on some kind of graph distribution. So graph distribution is important. You should be able to know which graph is required for which kind of work. And after that, you should able to have a knowledge of the calculation part. Like you should be able to calculate some of the part. Like this calculation required you to differentiate. Like it could be partial differentiation or it could be normal differentiation. So you should able to have a little bit knowledge about calculus and vectors. So it is not required in with extensor, but you should be able to know that. So polymaths you should able to eat like more graphs is going to be the basic stats in the probability one. So this is going to be sigma or mu on the basis of that. After this, I will just look into what you have to do based on after this is, which is basically you have to understand about the ML language, like as a programming I'm talking about, like the Python if you use. So how you are going to write this code in Python, it is going to be a bit of the understanding of the language and the frameworks you going to use for that. There are many kind of frameworks available on GitHub, and you can find many of these frameworks regarding the the specific tasks you are going to be using for specific like the work you have been given. And one of the like more popular frameworks like for like one of the things is like pandas you heard. So pandas what they do is that they use this framework to basically give you the give you the proper control over a data set. So it could be from CSV, or it could be from SQL data table, and it could be many kind of database you have, and you are able to connect and use it directly in your ML project with various processes or features they have for the framework. So you should be able to understand these kind of things because the coding part is bit a regress to do in one go. I am trying to do for me. I am trying to do learn this type of coding part in C++. I am thinking of doing it because C++ give you more control over what you should be able to write, and you are more able to understand more part of the code because of that. And you can use Python for that also, but Python has framework, so it doesn't make sense to use it. And Python, the frameworks if you use, it's almost the same as if you normally write the code for that, because the function will also produce the same kind of way of like if you are normally using what you should be using for normal like coding part, like the time complexity or any kind of things is going to be pretty similar, like it will be pretty similar, or because the same for Python, like if you write on your own. For C++, it is going to be wildly different because C++ is pretty memory efficient and a fast for language because it deals properly with the modules. So first we start with simple linear regression. So why it is called simple? Because we only use one factor, which is x here. And what is this linear regression basically? So linear regression is one thing we should know that about, like any kind of prediction we want to do is based on some kind of straight we are going to be making on this. Are you able to hear me now? Okay. So simple linear regression here basically it means that you are trying to do the regression here, and the simple regression part, what this means is that in regression, like you should know about, like you are trying to fit a line. It could be like a curved line, or it could be any kind of line, or it could be any kind of line you are trying to implement in some kind of way. So it basically means that you are giving out yourself a like you are basically giving out yourself like a line where like you should be able to predict something based on the data points you already know, or like outcomes you already know, and this line is the only way you can do it. So there is no other way you should be able to like change the line after you have done the prediction, or like you have made the line, and there is no certain way you should be able to change it in the future. So this is the main part of that, because it should all this is also one of the downside for this, because in if you see on the regression models, the simple regression models, they are able to produce good results on some of the parts of the data, or like some part of the work, but perform way worse in the other parts of the data. So start of this, like it's pretty simple. So what I have written is predicts the numerical outcome of y based on one factor x is using a straight line. So we know that we are forming a straight line here. So we are regressing y on x, y onto x, and this is a mathematical part. The y onto x function here it is written. So this is the relation part of that. So in simple regression, y is onto x, so you should be able to know about this in some of the important concepts for this here. And what we write that we are regressing y on x, so we write it as y is approximately equals to beta naught plus beta 1 x, let's say. So we are regressing y on x. So this is the simple uh, things we can write for one factor of x. So predicts a numerical outcome y based on one factor of x, assuming a straight line relationship. So y is approximately equals to beta naught plus beta 1 of x. So here we have given this, and firstly what we are trying to see, what we see is that beta naught and beta 1, what are these are model coefficient parameters. So these are a model which you are trying to build, and these are coefficient parameters for that. So it could be our training data, so beta naught cap and beta 1 cap. So this is what is the estimated parameter for that. So we are trying to estimate that. So we will see that estimated parameter in bit. So what we are trying to do the prediction here is that y cap prediction of this is equals to beta naught cap, so plus beta 1 cap into x. So this is the prediction part. So y cap equals to beta naught cap plus beta 1 cap into x. So this is the prediction part we have written. So this is the same as what we are trying to write here in the approximate part. So we can write this approximate as this, or you can write this approximate for removing is y equals to beta naught plus beta 1 into x plus psi. So this psi is here is error, and this is the model error you get. And this is one of the things that it is important to know, that there is always some kind of errors in any kind of noise in the data, is always there, and this is normal, and this is actually required to do. And you can see some of the proofs on YouTube also, like how this noise is actually has impacted on the symbol regressions. So we will start with this, like this estimated value. So this caps basically represent the estimated value. You can see on notes here also, and the training data we are getting, and we will use this training data to estimate this parameters of our, and the model coefficients we have, and the training data we have. So after this, what we will do is the model coefficient parameters, and we will try to estimate it using that. So estimated or estimation of this parameter, first is by estimation of the parameters by least square. So by least square is that we will use estimation here based on the measuring of the closeness of the points. So what is estimation of the parameters of least square we mean? The least square here we means is that ei equals to yi minus yi cap. So this is the estimation we are trying to do. So what this actually means is that, let's take this as an example. So we have given TV and the sales as x and y plots, and we have drawn a line. So how this line is drawn is based on these points, like we take, and we will drop a perpendicular over these lines. So after the perpendicular has dropped on these lines will give us ei. So this ei is nothing but yi, the points we are getting, minus yi predicted. So the points where the drop points is that. So this is yi cap. So this is the predicted point, and this is the actual point, the yi it is actually it has. So this is called the by least square method we are trying to predict. We measure the closeness for that. So for n observation pair, so we will calculate the residual sum square. So this residual sum square, or we can say it as RSS. So this RSS is equals to e1 square plus dash 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 2, you can say to till n. So we have the n points that we have. So we have taken n observation there. So this is going to be the residual sum square. e1 square plus e2 square plus till en square. So this gives us residual sum of square. So we have to minimize this residual sum of square to get the actual prediction we are trying to do. To minimize this, what we can do is that we have seen that it could be minimized using some part of our knowledge about uh, differentiation, and we can do one more thing is that we can find that beta 1 cap here. So the slope going to be here. So the slope going to be here is basically that the sigma of like all the points we will take, and we will take xi minus x dash and yi minus y dash divided by xi minus x dash to whole square. So the x dash and y dash here is slope means, so xi divided by n and yi divided by n. So these both are slope means, and we know that beta naught is going to be found by y cap minus beta 1 cap minus x cap. So we have found beta naught and we have found beta naught using beta 1. So uh, we basically are able to found this by least square method we have seen, and like it is a part of the residual sum square method, and we will see this method more pop up in next of the things. uh, it is an important point to note that for an observation pairs, the least square method is preferred sometimes over more of the things when you do a simple calculation. So you should do least square method as a starting part of a simple rather than any other model, so you do in any kind of way. So after that we will try to do a accuracy of the coefficient estimate. So how we can do the accuracy of the coefficient estimate? So firstly you should know that this beta 1 and beta naught we have found, it is estimated for us. So this estimation is based on like beta 1 cap is sigma of xi minus x dash into yi minus y dash divided by sigma of xi minus x dash to whole square. So this is the beta 1, and beta naught we will find using cap minus beta 1 cap to x cap. So this is the beta naught value for that, and here x dash and y dash is basically the slope mean. So we know that this is the predicted value, so there is some kind of accuracy we have to do because the prediction can be vaguely off from what the actual data point is actually is. So we can also see that if there is some kind of noise is there, so there is going to be very far away from the point where the noise actually is. So accuracy will be dependent on like y equals to f of x, like any kind of function we are writing in x to sigma. So this f of x is actually the regression part. So this f of x is any kind of f of x we write here is actually the regression part, and some kind of noise we have. So there is population regression line. So it could be contoured like this, and it could be 3D plot, like if you plot RSS beta naught and beta 1, so it will look like this, some kind of things. So it is actually in 3D plot also. And if you see here, when we plot this in normal like a class 2 regression like things, so if we see that this is the least square line, this is the population regression line, and this is the class 2 regression line. So we get different kinds of regression line based on that. So what we can do is that we will sample mean provide good estimation of the population mean. So the sample mean provides a good estimation of the population means, and the average mu over many data set of mu naught we get that. So there is one which is called as standard error. So we will denote this standard error as SE, and the average amount of estimate of mu naught differ from mu. So this is the definition of the standard error as you see in many of the textbooks. We, what it basically mean is that how much mu differs, like the mean value differs from the estimated mean value we are trying to do. So the sample mean provides a good estimation of the population mean. We should always know that a sample mean provides a good estimation of the population mean. So the average mu, like the mean we calculate over many data set, will give us mu, like a mean value, and this mu have an average standard error. Have a standard error, and this standard error of mu cap, or you can say standard error mu cap of square, is the variance of mu not equals to sigma square divided by n. So sigma here is the standard deviation, and the sigma square we called it as a variance of psi, the error, the variance of the error. The sigma square equals to variance of error. So standard error of beta 1 cap square equals to, or you can say the variance of beta 1 cap is sigma square divided by sigma of xi minus x dash square, or and the standard error for beta naught is equals to sigma square into 1 by n plus x dash square divided by sigma of xi minus x dash square whole square. So this is the beta 1, and this is going to be beta 0, and this is going to be beta 1. So beta 1 for the standard error of beta 1 square is equals to sigma square divided by sigma of xi minus x dash square, and you can also call this the variance of beta 1 cap, and standard error of beta naught cap of square equals to, or you can call it as variance of beta 1 cap is equals to sigma square into 1 by n plus x dash square divided by sigma of xi minus x dash square. So what we have seen is that for the standard error, we will compute one thing. It is called as confidence interval. So what we have to do here is that after that, we will do a confidence interval for that. So if one thing is also important, that if the standard deviation is not known, or like you can say the variance is not known to us. So if the variance is not known to us, so what we will see is that we can use RSE. So this is called as residual sum of square. So basically you have calculated the RSS, the residual sum square, and we can use that here also. So RSE equals to just nothing but root under RSS divided by n minus 2. So this gives us the residual sum sum of square. So this is the standard error of the beta 1 cap we are getting from this, and this is a good way if you don't know the sigma square, and you know that you know RSS but you don't know sigma square. So this is a very good way to calculate the residual sum. So for the compute of this standard error, so how we can compute this standard error? We can compute it using a confidence interval here. So we should know that what is this confidence interval in the statistic. So 95% of confidence interval means here it means range where the true population where true parameters lies with 95% probability from the population. So beta 1 cap plus minus twice of uh, standard error of beta 1 cap. So this is the true population means you should get for a confidence interval. So uh, not means like standard error for the beta one. So it means that the true parameters lies within the 95% probability from that population. So for that, if you want to see in the graph, so this is the 95% confidence interval. So this part it is called as 99% confidence interval. So this remaining areas are like alpha and s1. Like you can use that test or like t-test also. So like there are different kinds of tests in statistics to help you find these confidence intervals for you. So 95% of confidence interval within the range within true parameters lies with 95% probability from the population. So beta 1 cap plus minus twice of standard error of beta 1 cap. So this gives us this actually the standard confidence interval for it. So after this we will use the hypothesis testing. So hypothesis testing on the standard error can be used to perform hypothesis testing. So we use the standard error for hypothesis testing. Why we use it? So we use null hypothesis for that. So null hypothesis is basically like we used h naught and h uh, like a, or like you can use any kind of variable you want. So h naught is basically here is that the row relationship between x and y, and h is that there is some relation between x and y. So h naught is beta 1 equals to 0. So you know that beta 1 going to be equals to 0, and h naught there is some relation between x and y. So beta 1 is not going to be equals to 0. So we will use statistic to measure the number of हम लोग का standard deviation of beta 1 cap is away from 0. So so we will see one thing is that in hypothesis testing we use null hypothesis here. So we use these statistics to measure the number of standard deviation beta 1 is away from 0. So we will measure the number of standard deviation. So it is the like the standard deviation which we get like in t test, like any kind of t test we get. So any kind of t test we get. So how much standard deviation is away from that? So you can basically see that as a t-test. So if you want to see it more clearly, I can show you. So this like this part of, like if you see, so this is the standard deviation. So this is the formula basically. If you see like a math lecture, this is the standard deviation formula. You will see these kinds of formulas there, and like it is basically means like you are trying to find the t-test here based on the standard deviation, if you know. So this is one of the things is that estimated minus value we hypothesize divided by standard error. So this is the test statistic. So this is the estimated value we have done minus value we have hypothesized based on the null hypothesis, and divided by standard error we have calculated before. The standard error we have calculated before is based on this what we have calculated before is based on the standard error here. So it could be beta 1 cap minus x if there is some kind of error. So it could be beta naught minus beta naught also, or divided by standard error into beta 1 cap. So it is not always 0 here, but most of the cases it is 0 actually here. And we should remember beta 1 cap minus x dash, or like standard error divided by beta 1 cap. So this is more useful to know about these kind of things, t statistics, or like the calculation of these becomes easier. So t distribution with n minus 2 degree of freedom, assuming beta 1 equals to 0. So the probability will give us as a p value. So if we take t distribution with n minus 2 degree of freedom, assuming beta 1 equals to 0, then the probability will give us p value. So the p value, if p value is small, then we will reject the null hypothesis, and which means there is a relation between x and y. So if the p value is very small, we will just reject the null hypothesis, and this is a relation between x and y will get. So the t distribution with n minus 2 degree of freedom, assuming beta 1 equals to 0, will give us probability of the p value, and the t as beta 1 minus 0 divided by standard error of beta 1 cap. So this is the null hypothesis we get. So we will take some break over here to see that after this we will look at the distribution and the overall accuracy of the model, how we calculate using RSA and mass statistics. So So this is 53-minute mark. So this is 53-minute mark. And we will continue our rest of the 3-minute mark. We will continue. So what we have to see here is that in this part we have left. So so basically, in simple way, what this means is that what we are doing here is the coefficient estimation. So firstly, we know that we are doing here is the coefficient estimation. So we will use least square method. So we will use the least square method from here. We will do the coefficient estimation, the accuracy of the coefficient estimation based on that. So what we are meaning is that uh, just a sample mean, we take and estimate a population mean, our regression line, like the beta 1 cap, we estimate the true hidden relationship between the population. So what we are actually doing here is that we just estimate what is the true relationship between the population we actually should have. Based on this, the mean sample we are doing. So we are actually using mu based on that. So the standard error here measure how much estimation a beta 1 cap would like vary if we took many different samples. So this formula here, the standard deviation for that, standard error, sorry, for that we get this like the variation, how much it vary. So more precisely, tell us how much data points of n is spreads like, or when data is more spread out, or like when data is less spread out. So this standard error tells us for that. Uh, for this confidence interval, after this we have seen about the confidence interval. So this is the 95% confidence interval, means that the range where 95% of the two parameters or the two population parameters lie. So we are sure about that. So with like 95% probability of that population that's live there. So we have some standard error for that, like the calculation for that. So like it is off by basically saying like we know that this answer is X, but I am off by like these two standard errors. The next is hypothesis testing. So when you see like you want to see the data, see if X actually affects Y or not. So if X actually affects Y or not, we will use a null hypothesis for that. Assume there is no relationship beta 1 equals to 0 and some relationship when beta 1 equals not equals to 0. So H alpha you can say. After that, I think we are all right? Uh, so after that, what we will see is that in our like uh, calculation, or like what we can say in our like seeing these hypothesis testings, after that we came across a neat statistics. This measure how many standard deviation or estimate is away from the zero. So like the standard deviation beta naught we have calculated is away from zero. Like it measure how much value it is like far away, like distribution of this. So n minus 2 degree of freedom we take, assuming beta 1 equals to 0. We will calculate a probability, or you can say the p-value. So the basically the p-value, if it is small, like it could be usually it is less than 0.05, though, so we will reject the null hypothesis. So there is relationship between x and y, So we know that there is a relationship between x and y if the p-value is small. So after that, we will get to the accuracy of the model. So overall accuracy of the model is based on like RSE, the residual standard error, and R square statistics. So overall accuracy of the model. So the quality of the regression fits the data is we will calculate the overall accuracy of the model. So these are all the accuracy of the coefficient estimate. After that, so RSE is basically the residual standard error. So average amount of response will deviate from the true regression line. So RSE is the average amount of response will deviate from the true regression line. So we have known about some response and we want to know how much this response will deviate from the true regression line is known as RSE. So the average amount of response that will deviate from true regression line is called as RSE. If like y cap is approximately equals to y naught, like it is the predicted value is approximately equals to the actual value. So what will happen here based on it? So RSS is nothing but sigma of yi minus yi dash. So it is if it is that, so RSS will be going to be 0. So RSE, what we will calculation is RSS divided by n minus 2. So this is the RSE. So this same part which we have calculated, these two are same. So RSE, the uh, the residual standard error, the amount of response that will deviate. So that deviation is actually calculated from RSS, the residual sum square method, and we use this in the formula here. So after that, what we can also see that if the model fits well, yi should be closely equals to yi cap is equals to yi, and we can also see r square, the measure of the linear relationship between x and y. So r square is basically the measure of the linear relationship between x and y. So this basically tells us that uh, after this we will see. So r square is the measure of the linear relationship between x and y. So this relationship is called as correlation of r square. So what this r square actually means here is first we should know about capital R square. So R square statistic is you can say it is a measure of proportion of the variability in y that can be explained using x. So variability in y that can be explained using x is basically what R statistics means here. So R square means here. So R square is calculated using 1 minus RSS divided by TSS. So RSS here is the residual sum square, and TSS is the total sum of the square. So TSS total sum of the square is sigma of yi minus yi dash square, yi minus yi dash not square. So total sum square. So this is 1 minus RSS divided by TSS is R square. So total, like the TSS here is the total variance in response to Y. So TSS is the total variance in response to Y. Yeah. And the RSS is the amount of variability left unexplained after the regression. RSS is basically the amount of variability that is left explained after the regression. R square statistic is close to 1. So when R, so this is the imply here. So when r square is going to be basically between 0 and 1. So when it is like close to 1, that it indicates that the larger portion of the variance is explained by the model. So more accuracy, like it is a larger portion of the variance is explored by the model, and if it is closer to then the smaller portion of the variance is explained. So what is this correlation also? So correlation here, it is denoted by small r square, like or you can say covariance of x and y equals to r, and this covariance is exactly you can say that r square is equals to capital R square equals to r square. So r square statistics is equals to correlation, and which is equals to r square. So the small r square, here the r small r represent the covariance of x and y. So we can see the covariance as sigma of xi minus x dash into yi minus y dash divided by root of xi minus x dash squared to root of sigma of yi minus y dash square. So this gives us covariance of x and y. So r square is exactly the square of the correlation, and so we basically use this to estimate the shared sign, or the uh, like uh, like the slope beta 1 if we take, and the correlation coefficient r always have the same sign. If x and y have positive correlation, your regression line will have positive slope. So this is the important thing you should know, that if x and y have positive correlation, like if they have positive correlation, this part is positive, and like this part is positive, then you should know that the regression line will always gives us a positive slope. So if we standardize our data, like the slope of a regression line would be which would actually equal to the correlation coefficient. So this is a important point. Like if we standardize our slope, and if you standardize, like if anyone would standardize their slope, means like one of the standardization is like subtract the mean and divide by the standard deviation, like the mean divided by the standard deviation. So that will give us the like the standardized slopes, and the slope of the regression line would actually be equal to the correlation coefficient we got. So that is one of the part, and like we will get r equals to 1, a perfect positive relation, all points are exactly on the line, so that is going to be r equals to 1. If r is negative, a perfect negative relationship, so the correlation between, so we know that the slope will be going to be negative. If r equals to 0, then no linear relationship at all. So we know that there is no linear relationship between them, so the correlation of x and y is not correlated, and there is no linear relationship. So we can say this is the accuracy which we calculate based on that. The next part we will see is the multiple linear regression. So in multiple regression, there are more than single parameters, or you can say predictors. Like there are more than, so there is only one x, x we have taken. So we know that it is going to be beta naught plus beta 1 into x1. So after this, what we are saying here is that we have taken more of these predictors. So these more of these predictors will contribute here. So and so that our function will now change to, so y equals to fx. So this will change to y equals to beta naught plus beta 1 into x1 plus beta 2 into x2 till to beta p into xp plus sigma. And this psi, you can say, or error, this is error is noise, and there are p predictors here. So any bj has an average effect on y, of 1 unit increase in xj, holding all other parameters fixed. So what this means is that if any bj we take, any kind of b3 or b4 or any kind of a, any kind of like we take predictor from this bunch and has an average effect on y uh, of 1 unit increase in xj. So how much like if we increase 1 unit in xj, how much effect this bj will produce on y is basically like that part of the thing we want to calculate. So exactly, like we can see that the sales part here. So beta naught plus beta 1 into TV. We know that the sales come from TV and radios and newspapers. So we can include these all in our like linear regression. So this will give us a regression model. So holding all other parameters fixed here means like we should fix one parameters and fix all parameters and basically other parameters like instead of like calculating all of these in one go, like we should basically like fix all other parameters and focus on one parameter at first. So regression coefficient bj estimate expected change in y per unit change in xj with all other parameters fixed. The predictors usually change together. So if the predictors change together, like there is ideal scenario when predictors are uncorrelated. So there could be like seen like when we do one thing and another source is doing another thing and they don't produce any correlation in that. But in real world there is highly we doubt that like there is not a correlation in any kind of these things. Like basically if you use Twitch, if you use TikTok, you should use or you are going to use different kinds of social media platforms as well. So we basically know that it is all correlated in some sense. So it is not an ideal scenario in most of the cases. So correlation causes problem. Like what kind of problems correlation causes here is that the variance of the coefficient sometimes increases. So variance of the coefficient sometimes increases more, and xj changes, everything changes. So xj when change, then everything will change. So variance when increase, the coefficient variance when increase is sometimes then that creates a problem, and the next problem is xj changes, everything changes. So these are the two things we should kept in mind. And regression coefficient we have seen. So we will just like we can see that the coefficient we will take is like the estimate predicted value will be going to be beta naught cap, beta 1 cap to beta n cap you can take. And we know that example like this is the p predictor response, like this is two predictors and one response, like this is x2 x1, there are two predictors and there is only one response over here. So we know that there is a plane and we will implement the this plane as such that we want to minimize this. So we basically we want to minimize this prediction coefficient. So we are minimized using RSS once again. So we will use yi minus yi cap like square, and we will use RSS using this, and we will just minimize this using the RSS function. So two predictors, one response, like this kind of thing. So some important questions we should know about this is that is at least one of the predictor x1, x2, xp useful in predicting response? So at least one of the predictors, like we have taken many of these predictor. At least like there is uh, at least one of the predictor from these bunch of the predictors which is actually useful in predicting response. How should we know that? So we will use testing for relationship here. So can use hypothesis testing here. So the hypothesis testing, the null hypothesis, we will get beta 1 equals to beta 2. So all the predictors is going to be equals to 0 versus we will use h1, which is at least one bj is not going to be equals to 0. So any one cannot be equals to 0. So that will give us the null hypothesis opposite part. So the first we will do is called as f test. So for this we will do f test. F test is basically RSS minus the f test is going to be TSS minus RSS divided by P divided by RSS divided by n minus P minus 1. So it is going to be RSS minus uh, so TSS minus RSS divided by P divided by RSS divided by n minus P minus 1. So f is when is closely approximately equals to 1, then there is no relation. If f is greater than 1, then yes, there is relation. Larger the f, stronger the evidence that the f is stronger, the evidence is stronger, then there is. The p-value here tells us how significant f statistic is. If the small p-value, then there is no significance, like how significant this f statistic test is actually is. So we use that credibility using a p-value. So if like less than 0.005, like if p-value, then we reject the relation, reject the h naught and the relation existence. So testing subset of people of predictors. So TSS to RSS naught is H naught of B, like if we take beta P minus Q plus 1 and equals to beta of P minus Q plus 2, like this two till P beta of P equals to 0. So the T test for individual predictors is equals to F test for Q equals to 1. So when F test, if it is done on Q equals to 1, then it will give us T test for individual predictors. The T test for individual predictors is F test for Q equals to 1. We get here, we should know. So here we are using F statistics for the prediction. So we are testing the subset of prediction, always remember that. And for the advantage and disadvantage of this F statistic is that when P is large, like P value fails, like if is large, like P value fails, like versus F test exists, and only 5% of chance of rejection H naught incorrectly when H naught equals to true. And the disadvantage here is that when P is greater than N, some predictors and observation, then F statistic can be computed. So model can fit. So alternatively methods are forward selection method and high dimensional settings method. So disadvantage is that when p value is greater than n, node predictors and observation, then f statistics can be computed and models can fit here. And alternate methods like forward selection method and high dimensional settings is more advantage over there. So deciding on important variables. So only significant predictors fit model with associative response, often associated with the subset of prediction. So what does it actually mean is that, so basically here it means that only significant predictor fits the model with associated response. Some predictors impact on that response more thoroughly, and some have a negative impact. So we often associate with the subset of the predictors we are initially started with. So challenges with the last predictor, that testing all of these predictors. So it will take like 2 to the power p of the model. Like if there are p predictors, like if you take two predictors at a time, then it will take about 2 to the power p of the model's prediction. So what we do here for the criteria, so we use statistical metrics like Melo CPs or or a, a kind information criteria or AIC we call, or Bayesian information criteria BIC will call, or existed R square. So analysis of reduced plots for the pattern. So automated variable selection methods जो रहता है. So like this method basically here, So automated variable selection method. So there are forward, backward, and mixed method. So there are different kinds of method we have. So there is forward method, there is backward method, and there is mixed method. So the forward method is that start with the null model and add variable in decreasing RSS most and repeat until the stopping row. So decreasing of the RSS most like value. So variable, like we will decrease the variable, like start with the null model and add variable model with decreasing of RSS of the most. So we take the first RSS, then second, then so repeat until the stopping line. So we used backward for there is one thing is that we can't use backward when p is greater than n. When predictors are more than n, then we can't use backward. Start with all predictors, remove variable with the largest p value. So we will remove that predictor variable with the largest p value. Fit model again, remove next significant variable, continues until all the remaining variables will have p value. Will have the p value. ठीक है ना? So like p value set threshold. So any kind of threshold we set for the p value, if all of them have the same, so we will just stop there. So for mixed, what we will use backward and forward both for that, and we will start with null model like if, and add the best fit. So remove if p value is greater than threshold. Continue until no new variable can be added and no existing uh, needed for removal. So we know that this is address. So we basically use both like the forward and backward here. So we will start with null model and f and add the best fit. If p is greater than threshold, we remove and continue until there is no new variable can be added or existed to the removal order. So this is called as address redundancy. This mixed method. So if we see again the F statistics we have taken, so there is an advantage and disadvantage here. Basically, we have seen below also. So advantage is when p values large and p values fails versus the F test adjusted. So p values fails at the large p values, like it fails to do something about it, and NFT statistics exist for that, and only 5% chance of rejecting the incorrectly where the H short is equals to true. Only there is 5% of chance for the F statistic. So disadvantage is then when p is greater than 0, more predictors than observation, then F statistic can be computed model can fit. Okay, so the next part of the session is the next part of the session is the model fit. So model is the numerical measure of the model fit. So like the how the model fits like actual data, it is we use it like there is overfitting, underfitting. So there are different kinds of things you should know about the model fit. So how is actually fitting is like numerical measure of the model fit is like lower RSC, better model fit. Like if RSC is very low, then the model fit is very better. So so at this point of time, we just see if RSC is lower, and this will give us that it is the better model. And if R square, basically R square is between 0 to 1, and if R square is closer to 1, then we can say that in multiple regression R square correlation between response y and the fitted model y cap, and add the fitted linear model maximum correlation compared to the other relation. other lines. So adding variable, the RSS decreases, and adding variable R square always increases, even weakly when associated. Then ever also RSS always increases. So adding variable RSS decreases, and removing variable RSS increases. So RSS always decreases. Sorry, RSS decreases, but R square always increases, even when weakly associated. Even if we have weakly associated, RSS always increases. So use RSS when adding, then comparing. Like when adding and then comparing, RSS should be used then. Like actual increasing, we know that, and actual decreasing, we know that. So RSE is nothing but RSS root under, like RSE is equals to root under RSS divided by n minus p minus 1. So correlation between response y and the fitted model y cap is like in multiple linear regression we get it as R square, and this is basically one of the most important part of this is that R square is calculated on training data. Example doesn't reflect performance, so it doesn't like reflects the performance, and like R square is basically trained on training data to know about the things about the model, like how it is going to be fit. So all lower RSC better model fit of that, and R square is basically 0 to 1, 0 to 1. Overfitting risk is variable that don't improve model fit significantly may lead to poor performance due to overfitting. So variable that don't improve model fit significantly, so that don't increase the model fit more and more, may lead to the poor performance due to overfitting. So use RSC when adding, like then comparing. So when adding, like it will increase, or when decreasing, then it is cross. So when adding like RSC, so interaction effect and non-linearity is like plotting residual data and reveal patterns. Like these are important things, like you should know about the graph terminology, like how it is affecting it and how it is done based on that. So next part is the prediction part. So prediction is done on three bases. First is uncertainty in coefficient estimate. The second is model bias, and third is random error, which is the sigma we are talking about from for the long while. So uncertainty in the coefficient estimate is basically a y cap we take beta naught plus beta 1 cap plus x1 plus beta 2 to like beta be like any kind of the least square plane we take is an approximation of the true regression plane we calculate, and we get fx like here, like the function, the linear function beta 1 plus beta 1 x1 plus 2 del beta p xp. So there are reducible error and irreducible error. So reducible error is inaccuracy in the coefficient estimate. So these are reducible errors. So inaccuracy in the coefficient estimate. So after that, like there is model bias. So linear regression assume linear relationship between predictors and response, approx of reality, like best linear approximation is true regular surfaces. So like note, there is like model bias is ignored for simplicity. Model bias is ignored like for simplicity, like we don't actually care about this, but it is there, like best linear approximation, like true regular surface approximation of the reality of that surface, like what we really assume, like linear relationship between predictors and response. So random error is sigma, even if the time, if the true regression function fx and the coefficient beta naught, beta 1 to beta p is known. One second. Okay then. So so the next is like the random error we are discussing. So even if there is true regression function like fx and the coefficient beta naught, beta 1 and bp is known, and like the response variable y can be predicted because of the sigma, like this is the irreducible error. So we can predict the true response variable y even if we know everything about this, because there is an irreducible error with every of this. So that is why there is a random error of sigma. So even if we know the true regression function like the fx and the coefficient like beta 1, beta and beta is known, and like we know that the response variable is y, and like we can be predicted because of sigma, because of irreducible error. So next is the two things, that is the confidence interval and the prediction interval. So confidence interval is basically the quantity quantify of the uncertainty around average value of the response for set of the predictors values x, and the prediction interval is basically to quantify uncertainty for the response of the single observation. They are widely due to the reducible and irreducible error. So the confidence interval and the prediction interval, there are two things of this. So confidence interval is basically the the uncertainty around the average, like the quantify, like the value we get for the uncertainty around a average value of response for the set of predictors values like the x we have, and the prediction interval says that uh, we quantifies like uncertainty for the response of the single observation, like any one observation we get. And if we doing it for the set of the predictors value, then it is a confidence interval. If we are for the single observation, then it is a prediction interval. And there is one more thing, that in confidence interval there is an average value of response, and in prediction it is for the single observation, and there is no average for that. And there are like prediction interval are widely due to reducible and irreducible error. So they are more wider, like they have more like gaps is more like in when you calculate this, they will be more wider. So lastly, what we have to see is that the other consideration in the regression model we have. So there is qualitative predictors, which is called as categorical variable. So what is this qualitative predictors? So these are like it could be any kind of predictors, like for example, like qualitative here means like there is two types of things, like there is quantitative and there is qualitative. So quantitative is like the numerical values we have, and the qualitative you can represent different kind of data with 0 1 2 3, like we can give them numbers, and these numbers represent the data. And we know that in qualitative predictors, which is also called as categorical variables, and like first is like if we see, so there is predictors with two levels, like there are two levels for that. So we take like one dummy variable we can take, like for qualitative predictors with two levels, like if xi is 1 is that the person owns a house, and if it is 0 then person do not owns the house. So we can like use a dummy variable for that. So we will like the model will be like y I equals to beta naught plus beta 1 into xi plus psi I. So beta naught will be the average response, like the baseline group, like non-owners, and beta 1 will be the difference in average response between the groups. So this is like the models we will be using for two levels. And the p-value for dummy variable test whether the difference between the group is significant or not. So this difference is significant or not is tested by the p-value is for the dummy variable. So if we use the p-value for the dummy variable, this tests whether the difference between the group is significant or not. If it is not significant, we will know it by the p value. So yi is beta naught plus beta 1 into xi plus sigma I. So beta naught here is the average response between the baseline group, the non-owner which we have, and the beta 1 is the difference in the average response between the groups. So it is between the groups, the average response. So predictors with more than two levels, if there are greater than two levels, then there are multiple dummy variables. So there are a lot more dummy variables are there. So if we have k levels, so we will have k minus one dummy variables. So we can take one example is a region like east, west, south. So north will be our dummy variable. So x I one we take is equals to one or zero. It is going to be the person is south if it is one, and if zero is otherwise, it is going to be otherwise. So x12 is equals to x1 is like x12 if it is one, then the person is west, and zero is it is otherwise. So E is baseline here in this part of the D2, and we take D1 where n is the baseline here. So what we can say is yi equals to beta naught plus beta 1 into x 1 I and 1 plus beta 2 into x 1 I2 plus psi I. So what this means is that in this that the beta 1 here is the between south and east we have, and beta 2 is between west and east we have. So there are two kinds of relations we have here. So F test can be test whether of the dummy variable are significant, avoiding on individual P test. So we can avoid here individual P test, and we can do directly the F test to whether to test whether uh, any of the dummy variables are significant here or not. So we just know that it is significant here or not. So there are then k level of predictors or k minus one dummy variables. So if there are with predictors with only two levels, so we will use p values, and if it is more than two levels, then we will use k levels like k minus one. So we will have mixed predictors if we have quantitative and qualitative both responses. So combine dummy variables for qualitative response predictors with numerical values for quantitative predictors. So quantitative, we know that it is going to be numerical. So what we will do is we will use dummy variable for qualitative predictors, but quantitative predictors will be going to use numerical values. So model is going to be y equals to beta naught plus beta 1, like such as income. So income is a quantitative, so we will just use quantitative beta 1 as a predictor here, and beta 2 into student, so student status, sorry, student status. So it could be one, we can represent it for like high status or like any kind of status you should give here, and zero for any other kind of status. So it could be like a status for a different kind of things, like it could be like a group which uses this different kind of scholarships or any kind of things, or any kind of things they represent. So we can you represent them with 0 and 1. So these are qualitative, so we used it for beta 2 based on that. So plus psi for the random ratio. So what we can one more thing we have to look at after this is the extension of the linear model we have. So in this extension of linear model, there are some limitation of the standard linear regression, and there is relaxing additive assumptions, handling qualitative variables, and non-linear relationships. So what this actually means is that in the extension of the linear model, we have these four things as important. Uh, so one of this is that the limitation of the standard linear regression. So in linear regression, like we assume that relationship between the predictors and the response or like response, like they are additive or linear. Like linear is one unit change in the predictor results in the constant change in the response, like means any change in the x for the beta 1 or like beta any kind of you could take is going to affect y in such a way based on that only. So additive, like additive here is the effect of one predictor depends on doesn't depend on the other predictor. So other predictor doesn't contribute to that thing, is it is going to not affect the additive part of that. So we just assume that. So that is the limitation of the linear. Next is the relaxing additive assumption. So we relax that additive assumption. So what we can do is that in interaction term, like x1 into x2, like we will combine these effects. Like in ads, like spending on TV and radio together have a synergistic effect. This synergistic effect means like the effect we get from both of this is synergics. Like if TV is showing ads, it also affects the radio, and if radio is showing ads, it also affects the TV. So it is a synergistic effect based on that. So we can write here model as beta naught plus beta 1 into x1 plus beta 2 into x2 plus beta 3 into x1 into x2 plus psi. So hierarchical principal interaction. The interaction terms include the main effect also include other. So like this is the relaxing of the additive assumption. So this is additive assumption which we can relax for that. So handling qualitative variables. So qualitative variables is the interaction between the quantitative and the qualitative variables enable various effects on categories. So predicting credit balance using income. So which is quantitative, and student loan, which is qualitative. So model will introduce based on that. So qualitative variables is also included in this part of like the discussion, which is the additive assumption we talked about. So this is also based on that. So we can see that the balance is beta 1 plus beta 1 into income plus beta 2 into students plus beta 3 into income into students. So this is the part. Then we have nonlinear relationship. So there is polynomial relationship regression. So polynomial regression is the incorporate higher order terms like x square, x cube to fit nonlinear trends. So like if x square, x cube to like non-linear like gas minus mpg horsepower. So we have linear like mpg is like this beta naught plus beta 1 into, or we can use quadratic like mpg equals to beta naught plus beta 1 into horse into power plus beta 2 into horsepower squared. And like we use polynomial terms like higher order term x square, x cube to fit the non-linear regression terms like non-linear trends. Like we know that if we include these square terms like or like any kind of polynomial terms, we are able to capture more of the higher degree of relationship. So we get that quadratic or higher degree capture relationship better. So we just plot this here. After we have problems, what we faced in this is the first is residual error analysis. So in residual plots residual against fitted value helps detect patterns. A random scatter is a good fit like u-shape issue with non-linearity. So non-linear transformation, example like x square or log x, like these are non-linear transformations. So this is the non-linearity part where like we can't have like so like U-shape issue or non-linearity issue. These are non-linear transformations. So these are issue with the problems with the linear regression. So residual analysis. So residual plots like plotting residual against value helps detect patterns. So the one thing is that we can do residual analysis to detect these kind of things. So random scatter letters. So this is a good fit. So correlation of the error terms. So this leads to the narrow coefficient confidence interval, misleading p values. Like p values we get is not good here. So detection is like for time series data and the plot residual over time. Like we can use time series, like we can plot residual times for that. So you can use you can see different parts of the code, or like example on YouTube they do this. Some like you, if you find a good like YouTube videos there, they did do these kind of things as at the start of the like data collection part, like the time series data and the plot residual over the time to see if there is a correlation of error terms or not. So these are caused by the repeated measures, because we actually like sample this in very different ways, like in real world, and there are many ways to sample many of the things. The next is like this also like correlation will lead to narrowest coefficient interval, which is really drastic for like the very bad for the simple regression, and non-constant variance of the error term. So what is this called as? This is called as heterosystivity. So heterosystivity is nothing but as error should have the same spread. If it gets bigger, it's called heterosystivity. So what is this heterosystivity? So error should have same spread. If it gets bigger, it's called heterosystivity. So error should spread evenly. So it is not going to be like if it's get bigger, like if error is going to be spread equally, and if this error gets bigger, like very large, so this is called as heterosystivity. So we can detection is using the funnel shape, like wide at one and narrow at bottom, like we can use that as a funnel like we see. So fixed like we use is weight loss square, weight least square method, or transform outcome variables. So we use these kind of things. So use like weight least square, or transform outcome variables. So these are different kind of things we use. So outliers we have is called observations with unusual large residue. So there are many large residues which like we get from the observation. They are known as outliers. We can use box plots also for detecting these. So residuals, or the studentalized residuals, which is greater than like any kind of three, we know that these are like detection. We can use that for standardized residual to like detect these. So effect are like RSC and R square. So these are actually effect on this. So higher leveraging points have unusual predictor value and online significant, analyze them carefully to ensure model readability. So this is actually a note, like if you want to basically the points which have prediction value, like significant detection value analyze, we have to look them carefully for the model readability. So we should know that the readability of the model is more careful based on the prediction we have done and we want to do any kind of. So we are able to see the linear regression for this. So we know simple linear regression now, and we know multilinear regression for that based on that, and we know based on this multilinear regression model different kind of things, and also after this we know how it impacts different kinds of variable or any kind of impact we have on different kind of like scenarios we have. So that is going to be all. So this is the linear regression part for this.